Okay, let's have a look at a group of hydrocarbons called the alkanes. They're known as saturated hydrocarbons because they contain carbon and hydrogen only, and the carbons and the hydrogens are all single bonded. They're soluble in non-polar solvents, generally insoluble in polar solvents such as water. The general formula for alkanes is CnH2n plus 2, where N represents the number of carbons in the chain for the alkane. So our simplest alkane is methane, and you'll notice that we have an ANE. The ANE represents the alkane. So we get the ANE from alkane, and that's transferred to our actual alkane. So from our formula, we've got 1 carbon, and then 2N plus 2 gives us 4 hydrogens. So methane is CH4. We can draw out the structural formula with our carbon in the centre, 4 bonds to 4 separate hydrogens. Our second simplest alkane is ethane, C2, and we put our 2 into the formula here, and we get 6 carbons, so it's C2H6 for ethane. And we can draw our structural formula in the same way. Now the way to draw that structural formula is to draw the carbons first and then fill in the hydrogens afterwards. Our third most simple alkane is propane. Once again we've got the ANE and the ANE on the ethane. C3 and 2 times 3 plus 2 gives us the 8 hydrogens. So we draw our structural formula with our 3 carbons and then we fill in our hydrogens off that carbon backbone. Now I've drawn 2 other formulae here for our propane. Our first one is called our condensed formula. And this is where we condense each aspect of the alkane. So we've got a CH3 group here, we've got a CH2 group in the centre, and a CH3 group on the end. So the common part for the alkane is to have a CH3, a CH2, and a CH3 at the other end. So that's our condensed formula. We can also do shorthand notation. So we get this inverted, or this little hat figure there. So we've got 1 carbon, 2 carbon, 3 carbon for our propane. And for that particular one, we don't draw all the hydrogens in. When we get to much more complex molecules, representing them in this manner will be much simpler. Our fourth alkane is our butane. 4 carbons, 4 times 2 plus 2 gives us the 10 hydrogens. Once again, we draw our carbon backbone, all single bonded, and then we fill in with our 10 hydrogens. We can draw our condensed formula as CH3. There's our CH3. And we've got 2 lots of CH2, 1 there and 1 there. And we also have another CH3 group on the end. So we have our CH3, our CH2, and you'll notice that I have put a little 2 in there to represent 2 lots of CH2, and then another CH3. And we also have our shorthand formula. In this case, we've got carbon 1, 2, 3, and 4. Now we can get a generic formula for our alkanes. We call our alkanes that are just straight chain, such as the ones that I've drawn, normal alkanes or N-alkanes. And our generic formula is, for our condensed formula, is CH3, and then there are M lots of CH2, and then another CH3 on the end. So let's have a look at some trends in alkanes. We've got our methane, our ethane, our propane. I've put an N-butane representing the straight chain. Pentane is number 5, so N-pentane. N-hexane, N-heptane, N-octane, N-nonane. All of them end in the ANE, which represents an alkane. So we could write our formula, so we've got CH4 for methane, which we've looked at. We can go right down to nonane, number 9, or 9 carbons. So 9 times 2 plus 2 gives us 20 hydrogens for nonane. Let's look what happens to the boiling points as we increase the number of carbons. So methane, minus 161.5. Ethane, minus 88.6 degrees Celsius. We move up 0.5 degrees Celsius for propane, 36 for N-butane, 68.7 for pentane, hexane just under 100 degrees, and heptane 125 degrees, and octane and nonane somewhere in the region of above 150 degrees for their boiling points. So we can say that as we increase the number of carbons, our boiling point increases also. And we find the same thing for melting point as well. So let's have a quick look at some of the uses. If our boiling point goes up and our melting point goes up, it means our physical properties change, and therefore the possible uses that we might have for our alkanes also changes. So if we look to carbon, if we've got between 1 and 4 carbons, the state is a gas. Between minus 161 and 0.5 degrees is our boiling point. So generally, those molecules exist as a gas. And these, our methanes, our ethanes, our propanes and our butanes, we often use, or we do use, as a fuel. Carbons 5 to 7, so pentane, hexane, heptane, exist as a low boiling point liquid, and we use those as solvents and also as fuels. If we've got between 6 carbons and 18 carbons in our chain, these exist as a liquid, and these are used as our fuels. So our octane for our petrol sits in here at 8 carbons. Octane, it's a liquid, we use it for petrol. If we've got between 22 and 24 carbons in a single carbon chain, still exists as a liquid, but a much more dense liquid and used as jet fuel. Between 18 and 50 carbons, this is a high boiling point liquid, and these are our diesels or our liquid lubricants, sometimes our waxes and our heating oils. And then we move to our 50 plus carbons in our carbon chain, and these are solids. We just bordered on the solids for the lower ones, that's why we've got the waxes in here. But if it's greater than 50 carbons in our carbon chain, it exists as a solid. And this is our petroleum waxes, our paraffins, and even moving up into our bitumens and tars.